Hello everyone, it's my honor to be here to present our CVPR paper, Lite DETR, an interleaved multi-scale encoder for efficient DETR. So this is our CVPR poster, and welcome everyone to go into the poster session so we can have a more in-depth discussion about this paper. And now I'm going to briefly describe the main idea of the paper. So first, this paper is about the efficient design of DETR-like models, and the main advantages of this paper is that first, it is very simple. It only needs dozens of lines of code change, so it's very easy to implement for any DETR-like models. And second, it is very effective. It can reduce the encoder cost by 15% while preserve most of the original performance. And third, it is very general. We have validated our efficient encoder design on a series of DETR models like deformable DETR, edge DETR, and Dino. And the left figure shows that the performance of our model, as we can see, after adding our efficient design, the computational cost has been reduced by a large margin. For example, for edge DETR, we reduced its computational cost from around 215 GFLOPS to around 115 GFLOPS, and we can observe that it happens on both the edge DETR, Dino, and deformable DETR, and the performance is very close to its original ones. And the main idea is that the encoder in DETR-like models that use multi-scale features account for around 75% of the total computation cost. So because of the excessive tokens in high-resolution feature maps, and we propose to update high-resolution and low-resolution maps in an interleaved way to save cost. And we also propose a key-aware deformable attention to predict more reliable weights. So what motivates us to do this work is that we find the computational cost in DETR-like models, especially in advanced detectors that use multi-scale features, are very high. So when we try to find out why the computational cost is so high, we find that first reason is the encoder. As we can see, if we reduce the multi-scale features from 4 scale to 3 scale in Dino, the total GFLOPS has been reduced by a large margin, especially in the encoder. As we can see, the GFLOPS has been decreased from 113.7 to 13.1, and the performance mostly impact the small objects. As we can see, the small objects per AP has been decreased by around 3 AP. And when we want to try to analyze the high encoder cost, we find that in the multi-scale resolution maps, the large high-resolution maps has excessive tokens. As we can see, the S4 is the largest feature map in the encoder. It accounts for 75% of the total tokens. So these excessive tokens will make the encoder computation cost very high. And how to solve this problem? We propose two designs. The first one is the interleaved updates. So as we can see in previous slides, the high-resolution maps has excessive tokens. So one intuitive idea is to remove these high-resolution maps in some cases, or to reduce its updating frequency. So in this high-resolution features, most of them are not informative and contain local details for small objects. So we propose to update these high-resolution features at lower frequency. As we can see in this framework, we use the low resolution map as Q and all the other resolution maps as key and V, so that the query tokens has been reduced by a large margin, and those high resolution maps will only be served as query to update itself at very low frequency. For example, after a times of low resolution updates, there will be only one high resolution update. And after this design, we also propose a key-aware deform attention to improve the small objects performance. As we can see in deformable attention, the attention weights are regressed directly from the query with a linear layer, so the query will not interact with the key to produce its attention weight. And we think that in our scenario, this may not be applicable because the attention weights may not be so reliable, as we have updated these high resolution and low resolution maps in different frequency. So we designed to calculate attention weights with sampled both query and key. So this is basically our design, and the left part is the original design, so it will not sample key. So we sample both key and query to produce the attention weight. And now I'm going to show some of the results in our paper. And the first one is on deformable DETR. We add our efficient design to the deformable encoder, and we find that the performance is maintained, and we reduce the encoder G-flows by like more than 15%, while only impact the performance by 0.1 AP. And compared to other works that build upon the deformable DETR to reduce G-flows, our performance is better than them, and our G-flows is lower. And we also apply our model to Dino and DETR, because our efficient design is very universal, unlike in previous works that they inject many specific design for a specific DETR model, or we do not inject any other designs that is mainly for one model. So when we apply our efficient design to Dino and DETR, we find similar results, that the performance remains while the G-flows has been reduced by a large margin. And we also conduct ablations to analyze each component of our model to see its effectiveness, and we see that each component accounts for some of the performance improvements. And we encourage the listener to have a more close reading of our paper to see how this component works. And for our proposed key-aware attention, we also visualize some of the results to compare with the original deformable attention to see its effectiveness. As we can see, the first row is deformable DETR, and the second row is KDA, and we can see that the sampled location is more focused on the important regions, like especially in these high resolution maps. These sampled weights are mostly focused on the person. However, for deformable DETR, when it goes to the high resolution maps, the sample weights will be very sparse and not focus on the important regions. So the same applies to this one, deformable and KDA, and we can see our sample weights is more reliable and accurate to focus on the important regions. And we also conduct more visualization results on other pictures, and this generally with the attention weights is much more accurate than the deformable DETR. So thank you for the listening.